Hello, everybody. I began this lecture ambitiously thinking we would go all the way through the next actual topic. Um, it turned out that I felt more comfortable just doing a big review of what is SO3, the matrix group, and SU2, and how we got to where we are, and also review a little bit about the parameter spaces. Basically, a review of what we did last time in a relatively short lesson. So this 25-minute lesson covers really the same stuff we did last time, just a slightly different order, a different level. I mean, a little more cursory. It's more of a review, but it's a little bit more of a repeat also. If you're really comfortable with where we were last time, just skip this lesson and go to the next one. Otherwise, enjoy. And the next lesson, we will begin our subject of homotopy. Okay, thanks. All right, so let's catch up with ourselves and step back and just take some pride in what we've done here. We have successfully figured out how to calculate every matrix that is a member of the special orthogonal group that represents basis transformations of a three-dimensional vector space. And here we have it. This is our formula. The formula meaning this upper matrix here. And we have this formula in terms of three coordinate parameters, theta sub 1, theta sub 2, and theta sub 3, which sometimes I write with a superscript, sometimes with a subscript. These aren't tensors, so it doesn't matter. We're just choosing whatever symbol is cleanest. And as you can see, every now and then we have a square there, so I like to have theta 2 hat squared. I don't like to do theta 2 hat squared, and I certainly don't like theta hat 2 squared. I don't know, maybe that's theta to the fourth. I don't know. Anyway, the point is we were able to do this construction in the last few lessons, and it really, I wouldn't say it was easy. It took a lot of insight. We had to understand the infinitesimal transformation. We had to understand the definition of exponentiation in terms of the exponential of a matrix, alpha I, xi. We had to be able to calculate what these xi's were. These were the generators, right? Generators, which were really a basis of the algebra, right? The basis of the algebra, basis of the Lie algebra. And we understand that the Lie algebra, as an algebra, it's also a vector space. So we really started understanding a lot. We understand the algebra is a vector space. Here's an arbitrary member of that vector space. We understand how to exponentiate it. The exponential is possible because we understand the power series, right? The sum over 1 over n factorial of, what did we do? We did alpha I xi to the nth power, right? The fact that we do this nth power, that's where we lean on the algebra property, which means we can take two elements of the algebra and find, all right, so let's look back at what we've done and take some pride in our work. We've accomplished something pretty remarkable. We now know how to calculate every matrix that lives in the special orthogonal group that is a basis transformation of a three-dimensional vector space. And of course, the fact that it's a basis transformation of a three-dimensional vector space is reflected in that number. And being special orthogonal means it's metric preserving, and it also tells us exactly which metric is being preserved. The Euclidean metric, that would be written as a matrix as 1, 1, 1, if we were to use matrix notation for everything. And the fact that it's special means it's the determinant of every element inside SO3 equals 1. And that's exactly what these formulas represent. Each matrix element can be calculated by a specific formula. And in order to calculate the formula, we now know we need to specify three numbers, which we call theta 1, theta 2, and theta 3. Those three numbers are processed to give us three normalized coordinates, three normalized coordinates,
theta 1 hat, theta 2 hat, theta 3 hat, and one sort of magnitude, which is the Pythagorean sum of the three coordinates that we started with. Of course, theta itself is the positive square root of this Pythagorean sum. These become then these coordinates, of course, are what live in three-dimensional Euclidean space and are given an axis each. Let's see, theta 1, theta 2. I guess theta 3 comes out of the board if we do it that way, right-hand rule. And now we understand that this is a manifold, which means we can set up charts from here and map into this coordinate space, and we can establish this mapping in such a way that it's 1-to-1 on 2, and this whole set of matrices is homeomorphic to this this Rn. You know, I need to say that a little bit differently. This whole set of matrices, meaning the entire collection of all the matrices that live in SO3, it's not homeomorphic to all of Rn. What it is it can be broken down into charts, right? And each chart is homeomorphic to Rn, where this would be theta 1, theta 2, and theta 3, right? And so I need another chart that overlaps, right? And it's homeomorphic to another Rn, where I like to think it's a totally different Rn, but it also has the same parameters, theta 1, theta 2, and theta 3. And so this region of SO3 will get mapped into, say, this region of this Rn, and maybe this region of SO3 gets mapped to, say, this region of this Rm. And then these two regions can be mapped into each other, right? So that's how all the manifold stuff worked, right? That was what was really important. The point is we're thinking about this space in terms of these coordinates, but it's not true that this whole space is homeomorphic to Rn. It's not. Only part of it is homeomorphic to Rn, but every part of it that you can identify is homeomorphic to its own little Rn, and then all these Rns can be overlap mapped to each other in a very smooth fashion. It's a differentiable manifold. So that's operating here. And the reason that's important is where we will, as we'll be reminded in a moment, when we actually study SO3, which is right here, I'm sort of re-depicting it, let's look at just one particular mapping where we take the identity, for example, which is in SO3, and we map it into R3, and we get it to the center of the R3 coordinate system. And we know it's in the center because we can just calculate, we can calculate all the values of everything. Theta, when you're at the center, is 0 plus 0 plus 0. So theta will equal 0. That is important because when these three are 0, then all of the hatted coordinates are 0. The signs are all 0, right? We did this last lecture. The cosines are all 1, so these terms are all 0. So all the off-diagonal terms are 0, and the on-diagonal terms that survive are cosine of 0, cosine of 0, cosine of 0, which is the identity. So what we discovered is then that by wandering around wandering around in this parameter space, what we noticed is that if I took a straight line and just went off and off and off into parameter space, because these functions here are periodic, what ends up happening is my equivalent wander here always comes back to the identity, right? So, I guess that's actually a poor way of drawing it, right? Because what I should say is, let me move. All right, so what I've done is I've sort of opened up the space here, and this is the identity element here, right? So if I wandered in a straight line in the parameter space, and I went on forever, anywhere along this line in either direction, what would end up happening is I would have some movement in this space, and I ultimately would come back to the identity and I would just retrace this loop over and over again, right? And that is true no matter what direction I wander off in the parameter space, right? No matter what direction I go, I will always leave the identity and return and follow the same loop over and over and over again. And the reason that's important is that means this is a compact Lie group. That's what it means by compact. What I notice is that sine thetas are all 0, right? So all of these sine theta terms go away, just like they did when theta was when we took zeros for all the parameters. So all the sine terms go away. But that's not true of the cosine terms. The cosine terms take a value of -1, right? So these guys here all become, let's see, they become 2, right? That becomes a 2. This becomes a 2. All these guys become 2, right? 2, 2, 2, 2, 2. Now what's interesting is the hats, right? The hat terms, since theta I hat equals theta I divided by theta, right? All the hat terms, when you wander down here, say you wander the other side of the sphere, exactly opposite this point. If I wandered over to this point, all the coordinates change sign. So all of these theta hats will change sign, right? So all of these theta hats will change sign because this guy changed sign. This guy down here is always positive, right? Because it's the Pythagorean square root, the positive square root of the Pythagorean sum. But notice that they always come in pairs, right? So that sign change cancels out. It's either squared or it's in pairs. So the sign change actually cancels out. So what you end up with is a non-diagonal matrix, right? Because this term here, for example, is 2 theta 3 hat theta 2 hat. So this term here, which is off diagonal, right, has a value. But its value is the same for theta 1, theta 2, theta 3, and minus theta 1, theta 2, and theta 3, right? The negative versions. So it's the same matrix. This whole matrix is exactly the same whether I take theta 1, theta 2, theta 3, or minus theta 1, theta 2, theta 3. And because of that, the antipodal points are identical. Now, it's only the antipodal points because if you look here, theta 2, theta 3 is still in there. The direction still matters. This matrix is going to change if I change theta 1, theta 2, and theta 3. But whatever change I have will be exactly the same. Whatever matrix I do have for a given theta 1, 2, theta 3 will be the same at the opposite side of the sphere. But every point on the sphere will in fact have a different matrix, or every point on any hemisphere of the sphere will in fact have a different matrix. So what this is telling us is that the opposite points of the sphere are in fact identified. So this point here is identified with, well, when I say this point, this point here is identified with that point there, and this point here, which I might do, say in red, is identified with, my pen is not quite thick enough, it's identified with that point there. Likewise, every point on one hemisphere is identified with the point on the other hemisphere. Now, the problem with that, of course, is that's not how these manifolds work, right? These manifolds are always, every one of these chart mappings are supposed to be 1-to-1 on 2, so it's a bijection, and continuous with a continuous inverse, right? Continuous with a continuous inverse. That's what makes this a homeomorphism. So the homeomorphism only exists for a limited region of our underlying space and only to a limited region of the plane, which I happen to draw as a sphere here. But that's not what's going on here, right? That's not what's happening. We're actually getting 2-to-1 mappings, right? Whatever point this is, it maps to a legitimate point here. But then if this was trying to be a manifold mapping or a chart mapping, I'd be in trouble because that point maps to there and it maps to there. So that's not 1-to-1, right? So with that in mind, what gives? You know, I promised a manifold. Why aren't we doing with the manifold? And the answer is, you know, this is actually quite convenient. What we're trying to do is we're trying to force this topological space onto R3 with a coordinate system as R3 being the coordinate system. We're trying to force it. That's exactly like trying to force the surface of a sphere onto R2. You can't do it because the poles, the north and south pole, no longer has a unique coordinate. If you try to do spherical coordinates on a sphere, right? If you're going to take some sort of sphere and you're going to try to map it into theta 1 and theta 2, where theta 1 is, say, the azimuthal mapping and theta 2 is the polar mapping. When you get to the poles, you're going to have an ambiguity, right? Theta 1, the value of theta 1 could take any value as long as theta 2 is 0. No, the other way around. If theta 2 is 90 degrees, theta 1 can be any value on this axis, right? That's the way it is. The point is, though, that doesn't stop us from doing it, right? We're okay with that. We understand the pole is a little bit special, and we still use the 2D map for the globe all the time. But the sphere is a manifold. If I just made a different chart that covered the sphere where the poles were here instead of here, I'd have two charts that would cover everything, and every point in those two charts would be 1-to-1, and they would just be missing 2 points. Every chart would miss 2 points. Well, the same thing is going along here, but it's a little more sophisticated than that. This is easy to visualize. Here we kind of had to wrestle out the fact that, well, you know, if I just keep going with theta 1 and theta 2, eventually I hit this ambiguous place in the coordinate system where antipodal points are the same. And what we noticed was that for SU2, the problem was even worse because every point on the sphere is not only redundant, they're all the exact same points, because now when we go to theta equals 2 pi, right, every point where theta equals 2 pi, we lose all of the directional information. All the directional information goes away, and the only thing that's left is this number, and that number has no directional information, which means every point on that sphere represents the same matrix, cosine 2 pi over 2, which is cosine of pi, which is -1 and -1, which means everything on that sphere corresponds to minus the identity in the underlying group. So this is a great example of a massively degenerate coordinate system. And it's kind of fun because these are when you talk about manifolds and you say, oh, you know, coordinate systems fail, and in general relativity, they talk a lot about coordinate systems failing. Well, you know, we're seeing this, right? This is a coordinate system that fails. A coordinate system is supposed to be 1-to-1. I give you coordinates, you can tell me what element of the underlying set we're dealing with. I give you polar and azimuthal coordinates, I can tell you where on the globe you are. And there's no ambiguity. Now, in this case, there is, well, you know, I guess that's not exactly right, because if I give you coordinates and it's on this sphere, right, I guess the problem is the other way, right? The problem is you give me a point on the surface of the Earth, and I will unambiguously tell you what the coordinates are, right? And that's a problem, because if you give me the opposite of the identity, I could give you anything on this sphere and it would work, and that would be a myth. I wouldn't answer the question the same way twice. Likewise over here, you give me any matrix that has theta, that for which theta equals pi, right? There's a lot of matrices out. There's a lot of coordinates that will give you theta equals pi. But if you give me a set of coordinates where theta equals pi, I could give you one of two answers, right? I give you one of two answers. In this case, I can give you an infinity of answers, an uncountable infinity of answers. Every point on that sphere would be an answer to where is the opposite of the identity. Now, the solution here is I can actually create a chart mapping that takes the opposite of the identity and puts it at the center and maps everything homeomorphic to that. And then we just say that the chart is limited to the region of space that doesn't include this sphere, right? It's an open mapping that doesn't include this sphere. And I have two charts, and the two charts will cover this entire thing, and every spot will have one coordinate in those two charts. Okay. And this was the QSL or U1 of the quaternions, which ultimately has the same mapping. All right, so we did all that, and now, so the bottom line is, this is a fundamental problem, right? In the sense that this group has the same Lie algebra as this group, right? The two groups have the identical Lie algebra, but when you try to map them, but this coordinate system is telling you something very profound. This is not the same behavior as this. Here, the entire sphere represents minus the identity, and it goes out to 2 pi, and here, this sphere, these antipodal points are identical, and it goes out to pi. So it's interesting that these are not the same groups. They're different. If they were identical groups, if this was truly isomorphic to this, then these two situations in the parameter space would be the same. Now, there's another thing we should, before we move on, that has to do with the way we talk about all this. This material here, what I've been calling the parameter space, you can also think of this as walking through and around the Lie algebra. This is actually the Lie algebra, right? Because remember, the Lie algebra, every member of the Lie algebra is going to be some number theta 1 times x1 plus some number theta 2 times x2 plus some number theta 3 times x3, where I should probably write it with the index up, and each element using the Einstein sum would look like that. So there I'm kind of being flexible with my indices. But that is a member of the Lie algebra. So when I'm wandering around here, I'm picking out theta 1, theta 2, and theta 3, but I'm basically specifying a member of the Lie algebra. So when I say I'm going to walk in a straight line in the parameter space, what I'm really doing is I'm walking in a one-dimensional subset of the Lie algebra, meaning I've picked theta I xi, and I'm really walking on some number a, theta I xi, and a is changing, right? So as a gets really big, I end up somewhere along this line. As a goes big in the opposite direction, maybe negative, I end up down here. But if I go from large negative a to large positive a, I just move along one line whose slope or orientation is defined by my choice of theta 1, theta 2, theta 3. So this is called a one-dimensional subset of the Lie algebra, or one-dimensional vector space of the Lie algebra. It's a sub-vector space, right? Because we're fixing it in one dimension. By fixing these three parameters, and just changing this, we're really moving on one line in the Lie algebra. So the parameter space and the Lie algebra can be thought of at the same time. And what's important is, as I move along a straight line in the Lie algebra, I end up coming back over and over again to the identity in the real space. So every time I end up, if I keep going, I'll always end up returning to the identity. And I'll also end up returning to minus the identity. In fact, no matter which direction I go, I always have to go through minus identity, identity, minus identity, identity. I have to go through both of them because this entire sphere is minus the identity. Notice that's not the case here. I hit this sphere. Eventually, I do get to the identity again, right? Okay, but that takes 2 pi. Every 2 pi, I get back to the identity. All right, so the point I was trying to make here is that when you think about moving through this parameter space, think you're moving through the Lie algebra, because every point in this parameter space, right, I could just stop and pick any point, that point there. Well, what is that point? Well, that point is some value of alpha times theta I x I, right? So what do? Well, it's linear, right? So I go alpha theta 1 x1 plus, right? I take that alpha and I expand this sum and I get this. These guys here now become the new coordinates, right? I just put them in green, right? And then what do? Well, then I exponentiate that. And what do I get? I get a group element associated with that. And this is a Lie algebra element. So that's how we can think of the parameter space and the Lie algebra. Different books will talk about it in different ways. Some of them talk about it as a coordinate space. Some of them talk about it as literally a representation, graphical representation of the Lie algebra. But it really is the same thing. And you should think of it as both ways. It depends if you want to think of this more like this is sort of an extended chart of the manifold of the topological group, or do you want to think of it algebraically? This is the Lie algebra, and exponentiation gives us an element of the group. It's all the same.
And that's actually an important way of understanding this. All of this subject has 2 ways of looking at it. The topological story of everything as a manifold, where this has open sets and this has open sets, and we understand this to be a chart. I call it an extended chart because, of course, it goes so far that the coordinate system actually breaks down on the boundary here. So you can think of it topologically. But then you can think of it algebraically, where this is actually a group, and this is the Lie algebra associated with the group connected through exponentiation. What makes this subject so important is this is the place where topology and algebra are bound together. Right? This is a place where this concept of continuous spaces, homeomorphisms, compactness, connectedness, all of those topological properties, and then there's all the algebraic properties, being a group, being an algebra, having a basis, right, being a vector space. These things are bound together in this subject, and that is exactly why this subject is so important. Because what we discover is that there are topological groups that have algebraic properties, and those algebraic properties may in fact be topological properties, meaning if I can find a homeomorphism between this topological group and another topological group, I can be certain that that other topological group will share the same algebraic properties. And if not, I need to understand the limitations of that. This is why the subject is so important, is it binds together basically like analysis and calculus and something as strange as group theory and vector spaces and things like that. So, and this happens from time to time. For example, the first time it really should happen is when you study vector spaces and you create a metric on a vector space that gives the vector space a topology. So that's called functional analysis. So that's another subject that marries algebra of vector spaces with the topology of vector spaces if you endow those vector spaces with a sufficient way of creating open sets. And that's what this is all about. You've got to be able to create open sets in the group. And those open sets have to be structured in a way where you can homeomorphically map onto Rn to call it a manifold. Anyway, so thinking of a parameter space and thinking of it as walking through the algebra is all part of binding these things together into one sort of intellectual package. Okay, so we've done some review here. In our next lesson, we're now going to talk about paths in this space, and we're going to start understanding how significant the distinction is between the fact that SU2 has a big sphere here and SO3 is just antipodal. We're gonna instead of saying, gee, that's different, we're going to actually come up with a very precise mathematical notion of the difference. Okay, see you next time.